Alright, let's solve example 4.4 for your understanding about the S parameter. So this is circuit shown with T junction, T shape, right? T shape, and then it has a resistor, resistors, and this circuit has characteristic impedance is 50 ohm. So it asks S parameter of this circuit. So as we know, so A1 is right. So A1 is A1 is, so if we have a two-port network, so wave coming in is A1, coming out is AB1 at port 1, right? And then wave coming into at port 2 is A2, and coming out at port 2 is B2, right? So for S11, you can get B1 divided by A1 when A2 is 0, right? So A2 is 0 means there's no reflection at port 2. So to do that, we connect the load with the same kind of resistance, same impedance as characteristic impedance, right? So we can put Z0, which is 50 ohm. So that, because this circuit is based on 50 ohm based, so there will be no reflection. This reflection will be 0, right? So A2 is 0. And then for this case, we take the ratio between A1, B1, right? So for this S11, so let's say we have this circuit is based on 50 ohm characteristic impedance. So we need to calculate Z in, so that S11 gamma 1, right? So which is G in minus 50 ohm, G in plus 50 ohm, right? So reflection coefficient when this port 2 is terminate with this 50 ohm kind of load, right? So this is a reflection coefficient, basically S11, right? When this is matched, at port 2 is matched, so to get the Z in, so we just do equivalent impedance of this kind of circuit, right? So first 141 ohm is connected parallel with 5856 ohm, right? So if you take these two terms in one resistance, and then this is R, it's 8.56 ohm. So G in $140.62 plus 8.6 ohm, right? So this will be, so this one will be 41.5 0.43, so basically G is 50 ohm, right? So basically this other component is intentionally designed to make 50 ohm for this G in. So what does it mean? G in is 50 ohm, then reflection is 0, right? So which is good, so no reflection at the input port. And then because this is structure is symmetry, S22 also should be 0, right? Alright, so which is good. S11 S2 to 0. S11 S2 to 0 means, so let's have this 2 ports. So wave is come, A1 come in, B1 is 0, right? Because no reflection. And then A2 is also 0. B2, right? When this is terminated with 50 ohm, right? So for S21, signal voltage from port 1 to port 2, right? You can calculate A1, B2 divided by A1, right? So incident field, incident voltage, and how much incident voltage is gonna transfer to B2, right? This is a transmission coefficient. So for this case, A2 is 0, right? So for this case, right, so for this S21, we connect 50 ohm to make A2 0. So we can start from this. But for this case, when this 50 ohm is connected, as I said, A2 is 0, and then B1 is also 0, right? Because of this is 50 ohm, right? So there is no reflection. B1 is 0. So A1, if we add A2, and then for B2 term, if we add B1, it should be same because this one is 0, right? So A1 plus A, this should be B1, this should be A2, right? So this is 0, this is 0, so it is okay, right? So A1 plus B1 is basically, right, normalize incident and reflected voltage. So this is V1 plus V plus, and then V2 plus and V2 minus. 2 is 0. V2 to 0 means V2 plus is 0, same meaning, right? So this is basically total voltage at V2 and total voltage at V1. So we draw this circuit again, 8.56 ohm, and then is connected with 50 ohm. The ohm. So basically, total voltage V1. This is total voltage V2. So if you take the ratio between that, then we will get the S21, right? Because it is a specific case. Because B1 is 0, right, for this case. So if we take this as Vx, so Vx basically (8.56) plus the impedance here, right? Zeq, 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 right? So this Geq is 41.43. This V1, V1. And then V2 is basically Vx Pagi multiplied by right. So basically Vx this is 8.56 ohm and 50 ohm, right? So the voltage here is V2, right? So that's why we can get this V2 from Vx. So finally, right, V1 V2 divided by V1. Basically 0.707. So simple math will give you this one. So this becomes S21, right? So for P in, so let's understand what does it mean by 0.707 of S21. So P in is A1 square divided by 2, basically V1 plus square to 0, right? So we have two-port network. P in. How much power coming out from this network can be calculated as this, right? So this is P1 minus P2. This is P2. This is A1. So this is basically S21 square P1 plus square to Z 0. So because S21 is 0.707, if we square of it, we have so half power, right? P out is half of P in, right? So only half the power is delivered to the output, right? So basically there is a resistance kind of dissipate, burns half of power of input, and then only half power will be out, come out, right? The half will be dissipate, burn inside the circuit registers, right? So because power to power ratio is half and the voltage ratio is at 0.707, so if we want to change to dB scale, right? So we don't want to say, S21 is 0.707. We always use a dB scale for this S11, S21. So if you want to change to dB scale, 0.707, and then we times 20, right? Or this is a voltage ratio, right? Voltage ratio, which is S21, right? S21 is basically ratio between the voltage, right? That's why we should put 20, or if we take power level half, right? 0.5, so we only put 10. So basically this is same, right? So this is power level, power ratio. So if we put power ratio, we only put 10 here, right? So both are providing minus 3 dB. So if we put it in the calculator, you will see minus 3 dB. So S21 in dB scale is minus 3 dB, and then you know the insertion loss, right? Insertion loss, because we put minus here, minus, so it's 3 dB. So insertion loss is plus 3 dB. So either way is okay. So same meaning, right? So what does it mean? So because of this circuit, this network reduce input power with 3 dB, so we call this is a 3 dB attenuator. So if we put 10 dBm signal as P in, then what we can do, what you can expect is 7 dBm P out, right? P in minus 3 dBm dB is P out. That's why 7 dBm. So this is normally used in RF circuit application to reduce the power to 3 dB. Yeah, for kind of simple drawing. So maybe let's say why do we need this kind of attenuator, right? So which may not look good, because why do we need to reduce the power, right? So maybe you can understand as this. So let's say this is PA. So PA has a 10 dB gain, which means increase 10 dB, right? So let's say input is 0 dBm, and then this PA make 10 dBm from this. So gain is 10 dB. And then we want to kind of excite the signal 10 dBm to some test circuit, right? Test circuit. But if 10 dBm is too high, so that with this kind of high power, this test circuit can be burned, right? So that to reduce the power from this PA, let's say 10 dBm, and then if we put 3 dB attenuator to 3 dB attenuator, same. So after this 3 dB attenuator, this will be 7 dBm, and then this is 4 dBm, right? If we put some circuit, So if this test circuit kind of can work with 4 dBm input, then we use this kind of some attenuator after the PA. So this is sometimes needed to reduce the power, because this power is too high, so that we can kind of provide kind of a reasonable range P input power for this test circuit. All right.